Hello, this is Richard Hammock's Calculus 1. Today we start Part 5 of the course, Integration. In Parts 3 and 4, we learned about derivatives, what they are, what they mean, how to find them, and what their applications are. We learned a lot about derivatives. Beginning in Part 5, we're going to turn that on its head, in a sense. Lecture 38, our starting point, is antiderivatives. And here's our plan. Given a function f of x, we certainly know how to find its derivative. From f of x, we apply a process called differentiation to get f prime of x. What we're going to start to do today is to run that process in reverse with a process called antidifferentiation or integration. Our goal is, given f prime of x, find f of x. If you know a derivative of a function, and maybe you've forgotten that function, can you go backwards and find that function whose derivative you know? That's our goal. There's some definitions that go along with this. A function big F is called an antiderivative of another function little f if big F prime equals little f. So for instance, if you've got a function big F of x and you differentiate it and you get a little f of x, that little f of x is called the derivative of big F of x. But this big F of x, it's now called the antiderivative of little f of x. So if you have a function and you differentiate it to get little f of x, that's called an antiderivative of little f of x. And again, that process of going from the derivative to the antiderivative is called integration. You would say you integrate this function f of x to get this function big F of x. And we'll talk about that process today. Some examples, and I've got this definition repeated here. A function big F is an antiderivative of little f if big F prime of x equals little f. So if you differentiate big F and you get little f, that big F is an antiderivative of little f. As an example, let's find an antiderivative of the function little f of x equals 2 times x. So we're looking for a function here, I'll just put a question mark there, where if you differentiated it, you would get 2 times x. And you probably don't have to look too far before you realize, oh, well, f of x equals x squared. Its derivative is 2 times x. So x squared would then be an antiderivative of 2x. But also, you could have big F of x equals x squared plus 1. Its derivative is 2x plus 0, which equals 2x. So that's an antiderivative of 2x also. And in fact, you could have big F of x equals x squared plus 5, or any other constant added on, and its derivative would be 2 times x. So there's a bunch of functions. Big F of x equals x squared plus c, where c is any constant you want. That's going to be an antiderivative of 2 times x. So you can see here that whereas if you took a function and you found its derivative, there was only one derivative, but there are going to be lots of antiderivatives to a function. The function 2 times x is going to have infinitely many different antiderivatives of the form x squared plus some constant c, where that c could be any real number. So the antiderivatives of f of x equals 2 times x are all of the functions f of x equals x squared plus c, where c is any constant. And I've got these graphed here. X squared plus c, that just looks like the parabola x squared moved up or down c units. There's a whole family of curves, of which I've drawn 4 of them here, a whole family of curves. And they're all of the antiderivatives of 2 times x. If you take the derivative of any of these functions, you get 2 times x. Let's look at another example. Let's find all of the antiderivatives of the function little f of x equals x squared plus 5 times cosine of x. So we could think of it this way. There's some function that we're looking for. I'll put a question mark there. And if we differentiate it, we need to get x squared plus 5 cosine x. If we could find such a function, it would be an antiderivative of x squared plus 5 cosine x. So let's think about what would go here. What would work? Well, you need a term on this function where if you differentiated it, you get the x squared, first of all. And, well, let's see. The derivative of x cubed, if we took that, that would convert to a 3x squared. You get an x squared. So you might, first of all, say, well, f of x is going to have an x cubed in it. But then the derivative of x cubed is 3x squared, not just the x squared that we wanted. But we could fix that by putting a 1/3 in front of the x cubed. Now the derivative of 1/3 x cubed is 1/3 times 3x squared, or just 3x squared. So the derivative of this equals the x squared. So that's good. Now we've just got to add on something here whose derivative is 5 cosine of x. Think of a function whose derivative is 5 times cosine x, and you've probably already got it. 5 sine x. The derivative of 5 times sine of x is 5 cosine of x. And then we could add on any c that we want. And we have a function, big F of x equals 1/3 x cubed plus 5 sine x plus c. If you take the derivative of that, you're going to get x squared plus 5 cosine x. So these are all of our antiderivatives of this little f of x function. So answer, the functions big F of x equals 1/3 x cubed plus 5 sine x plus c, where c is any constant. Those are the antiderivatives of x squared plus 5 cosine of x. Now that we've seen a couple of examples, I'll introduce a definition and some notation to describe what we've been doing. Imagine you have a function big F of x plus c, where c could be any real number, and its derivative equals little f of x. Then we call this set of functions big F of x plus c, again where c could be any number, the indefinite integral of f of x. So that big F of x plus c, it stands for all antiderivatives of f. And that is called the indefinite integral. And sometimes maybe we'll get a little sloppy and call that just the integral of f of x. But technically it's the indefinite integral of f of x. And there's some notation for this. This big F of x plus c that stands for all of the possible antiderivatives of little f, that's denoted this way. You have an elongated s, which is read as the integral, and then the f of x, and then that's punctuated by a little dx, and you would read this as the integral of f of x dx. That notation stands for the set of all antiderivatives of the function little f, all of the functions big F of x plus c, whose derivatives are little f of x. And at first this notation may look a little strange, but you'll quickly get used to it. For example, the integral of 2x dx, we know that that stands for the set of all antiderivatives of 2x. We work them out on the previous slide. That's x squared plus c. So the integral of 2x dx equals x squared plus c. Likewise, think of the integral of x squared plus 5 cosine x dx. That stands for all of the antiderivatives of x squared plus 5 cosine x. And again, we work those out up here. So this is 1/3 x cubed plus 5 sine x plus a constant. So we'll see a lot of other examples shortly, but I want to point out this dx that's right here. For now, you should think about that as just like a closing parenthesis. The 2x is enclosed between the integral sign and the dx. Integral of 2x dx equals x squared plus c. And we'll say more about that dx shortly, but for now, when you're doing the exercises, just write it. It's part of the notation, just a punctuation. Okay, so we have these two processes, differentiation and integration. Given a function big F of x plus c, you can differentiate it to get its derivative, which we'll call little f of x. And then you have a reverse process of integration, where you could take the integral of little f of x dx and get you to big F of x plus c. Always remember that the integral of f of x dx, it stands for all the antiderivatives of little f of x. If that's equal to big F of x plus c, that just means that the derivative of big F of x plus c equals little f of x. The integral of little f of x dx, if it's big F of x plus c, if you differentiate that, it gets you right back to little f of x. I'll give you a few examples of this. Think of the integral of x cubed dx. It would have to be a function big F of x plus c whose derivative is little f of x, whose derivative is x cubed. And if you think about that for a moment, you'll see, oh, it's 1/4 of x to the fourth plus c. The integral of x cubed dx equals 1/4 x to the fourth plus c. The reason being is that if you differentiate this, derivative of 1/4 x to the fourth plus c, you get the x cubed. So you see how this and this are connected. Integral of x cubed dx stands for all the antiderivatives of x cubed. They are 1/4 x to the fourth plus c because the derivative of that, sure enough, is equal to x cubed. Here's another example. The integral of 2x over 1 plus x squared dx. The answer is going to be a function plus c whose derivative is 2x over 1 plus x squared. And you might not think about it right away, or maybe you would, but the answer is ln of 1 plus x squared plus c. The reason being that if you differentiate this ln of 1 plus x squared plus c, you've got to use the chain rule to differentiate that ln of 1 plus x squared, and you'd put the 1 plus x squared on the bottom and the derivative of 1 plus x squared, which is 2x, on the top. And there you go. The derivative of ln of 1 plus x squared plus c is 2x over 1 plus x squared. And that confirms that this integral holds true. The integral of 2x over 1 plus x squared dx equals ln of 1 plus x squared plus c, because the derivative of this answer gives you what you're integrating. Another example, the integral of 1 over 1 plus x squared dx. Looks almost like what we did before, except there is a 1 here where previously there was a 2x. This answer is going to be a function plus c whose derivative is 1 over 1 plus x squared. And if you think over your derivative rules, you'll see such a function. It's tangent inverse of x plus c. Because remember, the derivative of tangent inverse of x is 1 over 1 plus x squared. And that confirms that this integral holds true. The integral of 1 over 1 plus x squared dx equals tangent inverse of x plus c, because the derivative of your answer equals what you're integrating. So in these three examples, we sort of reasoned backwards to figure out the answers. And of course, what we really need is a set of rules for integration that tell us how to find various integrals explicitly. And one of the first rules that we'll encounter is what's called the power rule. And we'll have a lot of these rules. This is just the first one. There's a power rule for integration that is the reverse of the normal power rule for differentiation. And I'm going to reason that power rule out here. It's going to tell us what is the integral of x to the n dx. And I'll first of all give you the answer. It is 1 over n plus 1 times x to the power of n plus 1 plus a constant. Now we can check that this holds true by differentiating this answer and seeing if we get x to the power of n. So let's check it. The derivative of 1 over n plus 1, x to the power of n plus 1 plus c would be, let's see, you'd bring down the power of n plus 1 by the power rule for derivatives. It would come out in front of the x, and it would cancel with this n plus 1 here, and then you'd raise x to the power of n plus 1 minus 1, which is just n. And then the derivative of c is 0. So all you're left with is x to the power of n. So we've just confirmed that the derivative of 1 over n plus 1 times x to the power of n plus 1 plus c equals x to the power of n. And that tells us that this equation is true. This is called the power rule for integration. It reads just as we said here, the integral of x to the power of n dx equals 1 over n plus 1 times x to the power of n plus 1 plus c. And I'll remark that this works only if n is not equal to negative 1, because if n were negative 1, you'd be dividing by 0 right here. So n has to be something else other than minus 1. So an example of this, what if you had the integral of x to the 5th dx? According to the power rule, we do the following. In this case, the exponent n is 5, so we get 1 over n plus 1, that's 1 over 5 plus 1, times x to the power of n plus 1, which is x to the power of 5 plus 1, plus a constant. And that works out to be x to the 6 over 6 plus c. And that's our answer. And you can check this by differentiating this answer, and you will get x to the 5th. So we got this integral by using our new rule, the power rule for integration. Another example, the integral of 1 over x to the 5th dx. Remember that you can write this reciprocal as a power. That's the integral of x to the power of minus 5 dx. So now that we have the integral of x to the power of n dx, where n is minus 5, we can use the power rule to find this integral. According to the power rule, we get 1 over n plus 1, and in this case that's negative 5 plus 1, times x to the power of n plus 1, which is negative 5 plus 1, plus c. And that works out to be, let's see, that's x to the power of negative 4, and it's multiplied by 1 over minus 5 plus 1, that's minus 1/4. So the answer is minus 1 over 4 x to the 4th plus c. Another example, the integral of the square root of x dx. Think of that radical as a power. It's x to the power of 1/2. So we're looking at the integral of x to the power of 1/2 dx. For this integral, we can use the power rule because this fits the form of the power rule with n equals 1/2. So according to the power rule, we should get 1 over n plus 1, that's 1 over 1/2 plus 1, times x to the power of 1/2 plus 1 plus c. 1/2 plus 1 is 3/2. So simplifying this, the reciprocal of 3/2 is 2/3, x to the power of 3/2 plus c. So there's our answer. Maybe you want to convert that to a radical, so 2/3 square root of x cubed plus c. Either one of these two forms is an acceptable answer. Keep in mind that we don't just use the variable x. Mostly we use x, but you might have this same problem with a different variable, and it would read the integral of the square root of t dt. So instead of a dx there, since the variable is t, you'd put a dt. And by exactly the same rules that we did here, the power rule for integration, the answer would be 2/3 square root of t cubed plus c. It would match with this one, but with just a different variable. We have more integration rules than just the power rule for integration, because any derivative rule in reverse gives a corresponding integration rule. I'll give you a list. Think of the integral of little c dx. This equals little cx plus big C, where the little c and the big C can represent different constants. And the reason this formula is true is that if you differentiate little c times x plus big C, you get little c. So for instance, the integral of 3 dx equals 3x plus c, and you can check that by differentiating the 3x plus c, and you get 3. That's right there between the integral sign and the dx. We also have the power rule that we introduced on the previous slide, and remember this works provided that the power n is not -1. So for example, the integral of x cubed dx is 1/4 x to the 4th plus c. Now, what would you do if n were -1? What is the integral of x to the power of -1 dx? Well, the answer would be a function plus c whose derivative is x to the power of -1, and you don't have to think too hard to find that function. It's ln of the absolute value of x plus c. Remember, we have a derivative rule that says the derivative of ln of the absolute value of x is x to the power of -1, or 1 over x. So this is how you would use the power rule if n were actually equal to -1. In that case, your integration rule works as indicated here. And you often see this as the integral of 1 over x dx equals ln of the absolute value of x plus c. Let's continue. Integral of e to the x dx is equal to e to the x plus c, because the derivative of e to the x plus c equals e to the x. Think of the integral of sine of x dx. That's a function whose derivative is sine of x. Maybe at first you want to say it's cosine x, but the derivative of cosine x is negative sine of x. So the answer here has to be negative cosine of x plus c, because its derivative equals sine of x. Likewise, we have an integration rule that says the integral of cosine x dx is sine of x plus c, because the derivative of sine of x plus c is cosine of x. Now, we don't exactly have a rule for the integral of secant x dx, because that would involve thinking of a derivative rule, the derivative of a function where the answer was secant of x. And we don't have that. There's no such derivative rule. But we do have a derivative rule that says the derivative of tangent of x is secant squared x. And that gives us this integration rule. The integral of secant squared x dx equals tangent of x plus c. Again, because the derivative of tangent x plus c is secant squared x. So here we're running all of our derivative rules in reverse. Likewise, the integral of cosecant squared x dx equals negative cotangent x plus c, because the derivative of negative cotangent x plus c is cosecant squared x. We've got two more trig functions to run in reverse. We know the derivative of secant x plus c is secant x times tangent x. So that means the integral of secant x tangent x dx equals secant x plus c. And finally, the integral of cosecant x cotangent x dx equals negative cosecant x plus c, because the derivative of negative cosecant x plus c is cosecant x cotangent x. So a whole list of rules on this slide. And they continue. We know the derivative of sine inverse of x is 1 over square root of 1 minus x squared. In reverse, that gives an integration rule. The integral of 1 over square root of 1 minus x squared dx equals sine inverse of x plus c. What if you needed the integral of 1 over 1 plus x squared dx? You're looking for a function whose derivative is this. We happen to know one. It's tangent inverse of x. So this integral equals tangent inverse of x plus c. So we're running all of our derivative rules in reverse here to get integration rules. And here's another one. We know the derivative of secant inverse of x equals 1 over the absolute value of x times the square root of x squared minus 1. So that gives us this integration rule. And typically the way this one works is that sometimes the absolute value right here looks a little artificial. So we're going to move it from here to there. So from here, switch that to over here. And you can check that these are equal. So we get the integral of x, 1 over x times square root of x squared minus 1 dx equals secant inverse absolute value of x plus c. So remember these, and hopefully it's not a whole lot to remember since you already know the derivative rules. We have the integral of a to the power of x dx, where a is a constant, equals 1 over ln of a times a to the power of x plus c. You can check that. You know the derivative of a to the power of x is ln of a times a to the power of x. So the derivative of this is a to the power of x. We typically don't use this rule a whole lot because our exponential functions tend to be base e, but every once in a while you might have an exponential function to a different base a. Notice that if a were equal to e right here, this would be the integral of e to the x dx, and we already know the answer, that's e to the x plus c from the previous slide. You'd get that here because on the bottom you'd have ln of e, which is 1. You'd get 1 over 1 times e to the power of x plus c, and that's just e to the power of x plus c. If you read the text, you'll see a constant multiple rule for integration. The integral of c times f of x dx equals c times the integral of f of x dx. And there's also a sum difference rule for integrals. The integral of f of x plus or minus g of x plus or minus h of x and so on dx is the sum or difference of the individual integrals of those functions. It's noteworthy that there is no product or quotient rule for integration. There's no rule that says what is the integral of f of x times g of x dx, because we don't know any expression whose derivative is f of x times g of x. So you don't get a product rule by running the derivative product rule in reverse. So this is our list of integration rules for now. We'll look at some examples. Think of the integral of 5x cubed plus 1 over x plus 4 over x cubed plus 7 dx. And we're going to work this out piece by piece. First of all, notice that this is the sum of 4 different functions. So that sum difference rule on the previous slide says we can break that up into a sum or difference, in this case a sum, of the integrals of all of these functions. So first of all, we have the integral of 5x cubed dx. Then we'd have the integral of 1 over x dx. And then the integral of 4 over x cubed dx. And finally, the integral of 7 dx. What can we do next? Well, right here in this first integral, there's a constant of 5 that can come out of the integral. So we get 5 times the integral of x cubed dx. We get that next piece right there. That 4 can factor out. So 4 times the integral of x to the minus 3 dx. And then plus this last integral. Now we can work out this first integral using the power rule for integration and keep that 5 right in front. The integral of x cubed dx is 1 over 3 plus 1 times x to the power of 3 plus 1. The integral of 1 over x dx we know is ln of the absolute value of x. Using the power rule again, we get 4 times, let's see, the integral of x to the minus 3 dx is 1 over minus 3 plus 1, x to the power of minus 3 plus 1. And then the integral of 7 dx is 7 times x. Remember, that was our first integration rule. And then we add a c to the end. Now, cleaning this up, we have 5/4 x to the 4th plus ln of x. This 4 times minus 1 over minus 3 plus 1 is 4 over minus 2, x to the power of minus 2, plus 7x plus c. And finally, one last little bit of cleanup here. Let's move that minus up to the top. And there's our answer. Now, I did this problem in a very long-winded way, trying to use as many of the rules individually as possible to show how they work. And maybe the first few times you work out an integral like this, you might do it the way I've done it here. But typically, you're going to get really fast at this. When you have this problem, you'll look at it and say, okay, first of all, I need the integral of 5x cubed. And in your head, you'll figure that out using the constant multiple rule and the power rule combined. In one step, you'll get 5/4 x to the 4th. Then you'll say, okay, I need an antiderivative of 1 over x. That's ln of the absolute value of x. And this one, you'll say, okay, that's 4 times x to the minus 3. So its derivative is minus 2 over x squared. And then I need the integral of 7. That would be 7 times x, because the derivative of 7x is 7. And then you throw on that ubiquitous c. So typically, that's the way you'll work problems like this, pretty much doing it in real time, skipping steps, and doing it very quickly. If you ever get confused, like maybe you want to bring that x to the power of 3 up to the top as an x to the power of minus 3 and then apply the power rule, by all means do that. Don't skip the step if you think you might make a mistake. Bear in mind that x is not the only variable you can see. You might have the same problem where the variable is not x, but it's y, with a dy at the end. You'd work that out in exactly the same way. Another example, the integral of pi times 1 over x squared dx. Well, that pi up on the front, that's a constant, so it can come out in front. So we get pi times the integral of 1 over 1 plus x squared dx. And think of your integration rules. What's the integral of 1 over 1 plus x squared dx? It's tangent inverse of x. So we get pi tangent inverse of x plus c as our answer. And I want to point out one piece of notation here, that a lot of times when you have the integral of a fraction with a dx at the end, that dx will come right on to the numerator of that fraction. So this problem might look like the integral of pi dx over 1 over x squared. You'll see that from time to time, so don't get confused by it. So that's about it. And we've done a lot. We've introduced a process of integration that's the reverse of differentiation. The integral of f of x dx equal to big F of x plus c simply means that the derivative of big F of x plus c equals little f of x. These are reverse processes. If you start here with big F of x plus c and differentiate and get here and then integrate, you get back to where you started. Likewise, if you're at little f of x and you integrate it to get here and then take the derivative, you're right back to where you started. Don't forget that x is not the only variable in the world. You could also have other variables like y or z and so on. It's important to get lots of practice with this. Work tons of exercises, do antiderivatives, because you'll need it when we move on from here next time. Do that. I'll see you next time, and goodbye.